Hello, everyone. This is Alex from Rollups, and we're going to talk about scaling, about rollups, about optimistic rollups, zk rollups, and how you can generally do layer 2 scaling with regard to smart contracts and how zkSync can help you specifically scale your application. So let's start with the rollups. So I assume you all followed the latest news or from Vitalik from his talks a couple of weeks ago about Ethereum roadmap being adjusted so that rollups get a priority lane, and rollups essentially are considered the default way to scale Ethereum. And this is based on the fact that the rollups are by far more secure than any other scaling solution we have. And ETH2 will essentially become now the rollup-centric platform, which is really cool. So there are two flavors of rollups which you can choose, which you can pick, and they have some different trade-offs. And I'd like to talk more about that. But first, an interesting thing about rollups is that they allow you to keep composability of the contracts. If you put something in a rollup, unlike Plasma and especially unlike payment channels or state channels, you can just have normal contracts which interact with each other. You can deploy them separately and just keep the same flow as you have on Ethereum if you stay within the bounds of the same layer 2 solution or the same rollup. If you want to interact between different layer 2s or between the layer 2 and layer 1, so you want to make calls from your rollup to some layer 1 contracts, this will also be possible. You will preserve this composability, but it will always be asynchronous. You will have to pass a message or send some funds and then wait for this operation to complete, and you don't know when it's going to complete. You will not have this atomic composability. That's why it's important to have an ecosystem which is self-sustainable within some layer 2 which you pick. But the communication to other layer 2s and to layer 1 can have also different properties. So let's look deeper into that and compare the two rollup families, the optimistic one and zk rollups. And if you're not familiar with the differences, I encourage you to read some comparisons which are available in form of videos or blog posts. I will send a link to the chat after the video with our take on this. But essentially, optimistic rollups are based on fraud proofs. You have some operators who can commit some block on the rollup contract, and this block can be invalid, can contain invalid transactions, but it will always be possible for an external observer to challenge that and revert the block. Whereas with zk rollups, whenever an operator wants to commit a new block, they must provide a zero-knowledge proof of validity before the commitment happens. So they can never move the rollup into an invalid state because the validity proof comes first. So it brings a very interesting set of trade-offs. So I want to highlight that this is really, really important to understand if you're taking a decision which rollup you want to use. Let's start with the most important one, that is security. So optimistic rollups rely on one of an honest validator's assumption. So if one of the validators or like one of all the observers of the rollup is honest and succeeds to submit a fraud proof, then the entire operation is safe, right? Because you will always be able to revert any fraudulent transaction. So this assumption is pretty solid. If you have a lot of validators or a lot of users observing the operations, it's kind of okay to assume that one of them will be honest. The problem is they not only have to spot the fraud, they must also succeed to deliver this challenge to Ethereum. And that means they need to mine this within the delay period, which is configured by the rollup security settings. Most researchers consider 1 or 2 weeks to be sufficient. So you must be able to submit your fraud proof within a week. And this unfortunately can fail. So this can fail by miners on Ethereum colluding, or some miner getting 51% of the hash rate and starting a 51% censorship attack on the network, and just censoring your transaction for 1 week, and then the rollup is finalized and they can withdraw and steal all the assets from the rollup. And the cost of this attack is relatively low. It's something like $256,000 per hour multiplied by how many hours are in 1 or 2 weeks. But you actually don't have to even spend that, because it's enough to show a plausible commitment to this attack to threaten other miners that their blocks are going to be reverted and actually force them into compliance. And this limits the total amount of funds which you can place in a single instance of an optimistic rollup to something like 30, 50, 70 million dollars, depending on the hash rate conditions. I will post a link to this attack description to the chat as well. You can check it out. But this is roughly the limitation. So if your rollup has less than a couple of dozens millions of dollars in it, it's probably going to be reasonably secure if you have a lot of validators or monitors. If you want to put a lot of applications in a single rollup and have them like composable as like one big thing in DeFi, this is probably not such a good idea. Whereas with zk rollups, you can put as many funds in it as you want, and it's going to be always as secure as the mainnet Ethereum accounts, with the cryptographic assumptions aside. So of course, we introduced some new cryptography with zk rollups, which can have some issues. Of course, there can be also bugs in the protocol. But that aside, and those bugs and those cryptography is pure math and can be audited beforehand. If the audit's passed and if everything was implemented correctly, then you have exactly the same security guarantees as the mainnet. It has passive security. No one has to do anything, because you can never transition to an unified state. So that's the biggest difference. The second biggest difference is that optimistic rollups require this 1 or 2 week periods for like the finality in optimistic rollups is 1 or 2 weeks, because you need to allow some period of time for challengers to submit the fraud proofs. And that means you cannot easily withdraw to the mainnet. If you have non-fungible tokens, you actually have to wait 1 or 2 weeks. If you have fungible tokens, you can use the help from external liquidity providers to accelerate this, but you need a lot of liquidity to be available. So it only will work for liquid tokens, and it will have a pretty large cost, because you will have 1 or 2 weeks of parked capital there. So you have to take this into account. With zk rollups, the withdrawals happen within minutes. You just need the time to generate zero-knowledge proof, submit it to Ethereum, and then you can immediately withdraw. And the finality is also equal to this small number of minutes. Third difference, which might or might not be important in your time, is that privacy is easier to implement on zk rollups, because of course we use zero-knowledge proofs there. So it's a native technology built in, kind of out of box. With optimistic rollups, it will be a lot more expensive, because you need to publish all the zero-knowledge proofs in entire data sizes to the rollup as pub data, and it's going to be 20 to 100x more expensive than a normal transaction on an optimistic rollup. So the last big difference is the way the portability of existing contracts is approached in both systems. And it used to be kind of a mainstream opinion that you can port existing Solidity contracts to optimistic rollups, and you can't really do this with zk rollups. And this used to be true until this summer, before certain primitives in zkP technology were available, specifically recursion, some other things, some optimizations in provers. But now this actually changed. So there are generic contracts on zk rollups, and they are generic to an extent where you can take existing Solidity code and you will be able to compile it and port to a zk rollup with like almost without modifications, or for most contracts, it won't require any modification. So we will publish something interesting about this in the coming weeks. But for now, let's talk about zkSync. This is the platform brought by Matter Labs. We are live on mainnet. It can be used for payments. We are currently going for a number of integrations, starting with Golem, Multis, Storage, a couple of other protocols, also integrating into wallets. And you can, like, if you need to scale payments, it's available today. You can use it immediately. It works with any Web3 enabled wallet. You can use Wallet Connect, you can use MetaMask, whatever works. And you can do a bunch of interesting things. So you can use it for airdrops. You can use it for making donations, such as Gitcoin grants. Last round and the next round are both running on zkSync, because you can send tokens not only to the users which are already inside the system, but actually to any Ethereum account, regardless of whether or not they are registered on zkSync before. And they can always claim these funds later and get them back to layer one, even if they don't completely control the account. Even if they can't send a message, call arbitrary contract function. We also have some interesting things like multi-sig supported out of box, and also recently atomic swaps. And you can also build things like payment links and a bunch of interesting things. So I encourage you to check out zkSync.io, and we have comprehensive documentation there, or reach out to us and we're happy to talk about this. But the next version of zkSync will actually contain smart contracts, and we had a demo integration with Curve. We've put the Curve contracts on zkSync. We manually transpiled them from Viper into Zinc, our smart contract programming language, which I'm going to talk about now. And you can check it out at zkSync.curve.5 and play around. It's fully functional. You can go, you will see your transactions on our testnet. Sorry, it's not yet on mainnet. And you can go and do swaps. You will get some test tokens. So really try it out. So what is Zinc? So yeah, as I said, zkSync 2.0 will support contracts written both in Solidity and in Zinc, and will probably, in at least in the beginning, in order to port Solidity contracts, you will need to transpile them in Zinc, which is a Rust-based language, which features type safety, type inference, immutability, safe math, essentially all the nice things from Rust, all the things people love in Rust. So if you tried Rust before and you didn't like it, don't worry, we stripped all the features which normally make people hate Rust. So it's not going to be complicated. It can be learned within a couple of days by Solidity developers. It's really easy. You can check it out at zkSync.io, and it's really it can be an opinionated statement, but you want to write smart contracts in a language which is as close to Rust as possible. So you need the type safety, you need the immutability. It really reduces the number of bugs which you can build in the contracts. And for financial applications, for highly secure systems, it's really important. This is why Rust is becoming so widely adopted by cryptography and by a number of other protocols, other blockchains, starting with Facebook, Libra, to Polkadot, to Alio, you name it. But it also has a very nice module system and a packet manager based on, or similar to Rust's Cargo, where you can do a lot of things from command line in a really nice way. So you can structure your code, you can have a code hierarchy, You can generate the contract, you can interact with contracts, you can deploy it to testnet, you can run your tests, all from this single packet manager, install dependencies, and so on, make formatting. And a couple of things which I want to highlight about Zinc is, first, it supports unit testing natively. You can write your unit test in Zinc, and it's very expressive and pretty convenient to have. Like a lot of things you really want to unit test before you do this large, heavy, long-taking integration tests. Then it supports debugging natively. You can make debug traces, and it's very interesting because these debug traces are not the part of the production code, so they will not bring additional overhead. And you can play around and do as many traces as you need, and you can actually have the traces on the live transactions, which will happen on the mainnet, and you can modify your code and rerun the same transaction and check in the log traces what was the problem. It's going to be really, really much easier to debug than Solidity contracts, which we had to deal for past couple of years. And yeah, so this is Zinc, but as I said, Solidity will be also a first-class citizen, and it will be possible to deploy things in Solidity. We will probably at some point support Solidity compiler natively. But in both Solidity and Zinc are going to be Turing complete, so anything that is possible in Ethereum will also be possible in zkSync, including composability. So the last thing I want to mention about zkSync is that it's going to be a decentralized platform with a broad set of token holders having control over it, and a smaller set of validators with a fast consensus, so that we have sub-second block confirmations, and essentially every transaction is going to be confirmed in less than 1 second, but in a decentralized way. So we're going to use something like Facebook's hot stuff consensus algorithm, which is really fast. It has optimistic fast finality and low latency. And it's very important to us. It's one of the core values at Matter Labs. All the contracts, all the participation in the consensus is going to be 100% permissionless. So there will never be a centralized party. So I mean, there is now a centralized party in the zkSync 1.0, but as soon as consensus is implemented, we're going to switch over it, and the network is going to be owned by the participants.